Okay. So let's see the proof real quick because it's really easy. The proof uses Markov inequality that you remember from your basic probability course. For any positive theta, non-negative theta, we can always take this probability and convert it by raising both sides of the inequality to the exponent. Like, I mean, that is taking e to the power both sides of the inequality for positive, non-negative, that is values of theta. This will be an identity, right? So, and then use Markov inequality, because the probability that this random variable, this new random variable, let's say y, exceeds this value, little y, is upper bounded by the expectation of y divided by that value. As you know, Markov inequality is in general a very loose inequality, but then we have this device theta that we can tweak, which is going to be the y, our bound is going to be strong. Now, since this inequality 3.28, this inequality holds for any theta, then we can always, sorry, let me just bring my screen back. We can always take the infimum over non-negative theta, which translates into this expression. Because, why? Because this expectation of e to the theta times summation xi is another way of defining the moment. I mean, this expectation, basically, we can always think of, well, m of theta, the moment generating function, is the expectation of e to the theta xi, and you can massage this expression to bring it to this form. So this is the Chernoff bound. And let's now see an application, immediate application to it, to networks. And this is where we will come to concept of statistical multiplexing. Okay. Now let's switch gears completely from discussing a probabilistic bound to a problem in networks. Consider a link with bandwidth 10 megabit per second, which is shared by multiple data sources. At any given time, the source is active with probability 0.1 and transmits at a rate of 100 kilobit per second when it is active. So when it is active, it is going to be transmitting at 100K. Okay, all right, this is the peak rate of the source, but it is not going to be active all the time. It's active 10% of the time. And all of these sources do this independently of each other. They are active independently of each other. So how many sources can you allocate to this link to satisfy their requirements? What do you think? Any ideas? I mean, clearly, the most obvious is if you allocated only, if you allocated bandwidth according to their peak rates, 100 kilobit per second, if you allowed each source a full 100 kilobit per second, you could support 100 sources. And they would never see a problem. They would always be fully accommodated, enjoy complete quality of service. However, you would be limited by 100 flows on this link. Now, can we do a little bit better? by
Hocam,
probabilistically allocating the link, such that, you know, each link is active only 10% of the time. We're being very pessimistic by allocating the bandwidth according to the peak rate. How about we allocated a little less for each source, and we sort of hoped that they're not going to be active all the time, right? So we could allocate more flows to this link. For example, how about we allocated 200 flows to the link? Okay, if we allocated 200 flows to the link, what would be the probability that the capacity overflowed so it couldn't support all of the flows? This probability you could compute actually easily if you assumed the sources are independently active or not, like Bernoulli random variables. This is easy. Like you could compute this exactly. But you could also apply the Chernoff bound, okay? Rather than do this exact computation. How about, right, so what is the probability that the sum of the xi's, where xi's are Bernoulli random variables, which indicate whether source I is active or not? You already know about, you remember indicator functions. I believe you probably do from your probability courses, such that the indicator function xi indicates whether source I is active or not. Okay, so the probability that the sum, so basically the sum of all the xi's gives us what? Gives us exactly the number of sources that are active. Okay, so then the probability of the number of sources being active exceeding 100, this probability is the probability that the link overflows. Now, Chernoff bound lets us bound this overflow probability. And if you put in the Chernoff bound for the binary case, which was this thing, compute the Kullback-Leibler distance between x and mu. Okay, x here is a parameter that we will use in our plots, and mu is, what is mu? Mu is 0.1. Okay, so for every given value of x, for example, suppose x is 0.2. Okay, because let's check here. Let's look at this plot. Let's look at the number of flows. N is going to be our parameter here. Oops. N is going to be our parameter. As N is swept from, in this example, 500 to 800 in steps of 10, I believe. It is plotted. For example, for n equals 500, we're computing the probability that I from 1 to 50, xi is bigger than or equal to 100. So in this case, x is 2. And what is mu? Mu is 0.1. Okay, and yeah. Oh, wait. I'm sorry. So let's go back to our bound. It says, right. Probability summation xi is bigger than or equal to n times x is less than or equal to this bound. So this is n times x. So x is 2. I was right. All right. So compute the Kullback-Leibler distance and compute the right-hand side. And here is what we find. This is the overflow probability bound. The overflow probability is below this. So it's even better. So we are guaranteed that the overflow probability is less than 10 to the minus 1 at 800 sources. At 750 sources, the overflow probability is not above 0.01%. Okay? We can even increase, if we allow an overflow probability of 1%, we can even increase the number of sources to 800. So that shows that by statistical multiplexing, we can accommodate a much larger network capacity, much larger number of users. And this is called statistical multiplexing. And it is being done in networks today, in almost all networks, in cellular networks, as well as in Wi-Fi, in the internet. Where is it not done? Think of legacy systems that this is not done. I mean, there may be certain military communication infrastructures, for example, where it is a dedicated circuit switched link is required. In the old days of public switched telephony, right? We have a circuit switched system where every user got a dedicated line, whether or not they use it. Okay, this is before the advent of essentially switching. So in those cases, in the old legacy systems or certain special purpose systems, allocation could be without any overflow probability. However, in almost all communication systems, we have statistical multiplexing today. Okay, so we have been able to achieve this increase in the number of users that can be supported through no use of any buffers. We didn't even use a buffer. We just allowed an overflow probability. We allowed certain flows to get rejected. And we were able to increase the number of flows that are supported. But how about now if we allow a buffer? Okay, if we allow queuing in the network. In order to understand queues, we will have to understand a little bit more. We will have to revise probability, especially the topic of Markov chains, in order to understand basic queuing models. So that is what we're going to do next. And when we understand Markov chains and basic queuing systems, we will then be able to compute average delay. Any questions before we do that?